Hello. This lecture will cover pages 91 through 99 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Combinational Logic Circuits Part B, Exclusive OR and Exclusive NOR Gates and their applications. So far we have discussed 6 different types of gates. If you remember the inverter or the NOT gate, we had the OR gate, we had the AND gate, we had the NOR gate, and we had the NAND gate, and we had the buffer. There's 2 more gates we have to talk about, and then we're done with gates. There's no more gates. That's all. You just build circuits with the 8. The 7th gate is called the exclusive OR gate on page 91. Its symbol looks like this. 2 input A and B, and the output is Y is equal to A bar B or AB bar. The truth table looks like this. Notice that it produces an output whenever the inputs are different. We talked about that in the previous lecture. It's called a 7486 chip. If you look in your specifications, you'll see the 7486, which is a quad 2-input exclusive OR gate. This is one of the symbols. You have to memorize the truth table. The symbol does not tell the story in this case, like it does all the other gates. You have to memorize the truth table for the exclusive OR, and then basically, if you just put a bubble on the output of it, you can come up with the last gate, which is called exclusive NOR gate, and it's written like this: exclusive NOR, and this is the symbol for exclusive NOR. It looks like the exclusive OR with a bubble at the output. And it presents an output Y is equal to A bar B bar or AB. Notice that's different from what we had up here. The way it's shown is A exclusive OR B barred. That gives you the exclusive NOR. And here's a truth table for it. Notice that it produces an output whenever the inputs are the same. That's these circuits, these 2 gates, exclusive OR and exclusive NOR, you need an output whenever the inputs are different, and you need an output when the inputs are the same, has many, many applications. If you look on page number 92, applications of exclusive OR and exclusive NOR gates include parity generators and checkers. We talked about parity, odd and even parity. I'll show you how you can use exclusive OR gates to generate parity for error detection now. Controlled inverter circuits, very useful. Comparator circuits, very useful. Arithmetic circuits, very useful. All these circuits, when you hear parity generators, or you hear controlled inverters, or you hear comparator, or you hear arithmetic circuits, if you hear any of this terminology, the design is using exclusive OR gates or exclusive NOR gates. That's a big hint for the exam. Anytime I ask you about any of this, you're looking at exclusive OR, exclusive NOR gates. First of all, let's look at a 4-bit parity generator and checker. That's on page number 93. And I want to give you an idea of what we have here. Let me find it. Here you go. Hopefully you can see all that. Here's device number 1, and here's device number 2. And this could be a computer, or this could be a modem, and the computer's generating information to a printer, or the modem is generating information and communicating to another modem. To make this easier to understand, I just put 4 bits here, 1, 2, 3, 4. Instead of a full byte, I just used a nibble. And this device over here, it has a parity generator inside. It generates parity. It generates a parity bit. And if you remember, what we're going to do is make this we're going to make this a lot simpler than we did in the 3rd lecture or whatever. We're just going to use a nibble. These are the bits here we're going to send over to device 2, and we're going to make parity bit that 5th bit. That's going to be down here. Let's give you an example. This device number 1 is going to generate a 0, 0, 0, 0. And let's say that when you receive it over here, it gets over here as a 0, 0, 0, 0. There's no error in transmission. So if you take a look at our error signal should be low. It's a high active error signal, so this device number 2 should see this error signal as inactive. Let's see if it does. Notice these are exclusive OR gates. And exclusive OR gates, you look at the truth table, it'll produce an output whenever the inputs are different. Well, they're the same here, so that gives a 0. They're the same there, that gives a 0. They're the same there, and that gives a 0. So the parity bit gone over here is going to be a 0. Let's just put it over here. That's the 5th line that goes over. Or it could be the 8th line or the 9th line that goes over. It's just generating an even parity bit. Notice it's generating an even parity bit. It keeps the total number of 1s even. Okay, there's no 1s, that's 0 is an even number. So when it receives the data, this device number 2 has a parity generator in it also, but it also has this parity, this extra exclusive OR gate that generates the comparative signal. So this circuit here will receive the same bits that this circuit did. So it's going to generate a 0. And if the parity bit was 0, a 0 and a 0 gives you a 0, which says there's no error because that's a high active signature. So this device knows that the data got over here accurately. Well, let's do something a little bit different now. Let's get rid of that. And let's generate an error. Let's put a 0 and say we get a 0 here, and say we get a 0 here and a 0 there. You can make up any bit pattern you want here. And we end up with a 0, 0, 1, 0 that's received. Clearly there's an error. Over here, a 0 and a 0 gives you a 0 and gives you a 0. It generates an even parity bit, which is 0. As it receives this data over here, it's taken the inputs. These inputs here come from inside the device. I just drew them out here so I could show you the circuit. Notice that these two are the same, so you get a 0 there, but these two are different, so you get a 1. Those two are different, so you get a 1. So that 1 and a 0 gives you a 1, says you got an error. It's a high signal, high active signature, and you got a high level. It's an error. This device knows you got an error. Let's do one more. There's a lot of possibilities here, but let's say that you had a 0, 1, 1, 0. Let's see what we generate. You know this is going to generate an even parity bit. Even parity is, it's going to have to generate a 1. It's going to have to generate a 0. Let's make it generate a 1 down there. Let's just make it generate a 1. The way we're going to do that is we'll do that. That's what it's transmitting. And what it receives over here, let's say it receives it, the same thing. So there's no error. Let's see if there is. A 0 and a 1 is going to produce a 1. A 0 and a 0 produces a 0. They're different, so you got a 1. So that 1 generates an even parity bit. Notice you have 2 1s now in the 5-bit stream. In the 5-bit word. This 1 comes over here. Over here it generates the same thing. A 1 and a 0 gives you a 1 down there, and a 0, 0 gives you a 0 there. That gives you a 1 and a 1. These are the same. So that gives you a 0, so there's no error. That's how you use exclusive OR gates to create a parity bit with a parity generator and a parity checker. The parity checker has to have a parity generator in it along with this comparator exclusive OR gate there. So try a couple other combinations and you'll see that this always works. Now, final comment here about parity. It doesn't make any difference whether you use even parity or odd parity. There's no benefit by generating an even parity bit or an odd parity bit. However, if this device is set up for odd parity, this device better be receiving odd parity. If this is set up for even parity, this device better be set up for even parity. That's important to understand. The other thing is, this only detects 1 error, or 3 errors, or 5 errors. It only detects odd number of errors. If you put 2 errors in this transmission, if you make this a 1 and this a 1, so that you have 2 different errors here, it won't detect that. It won't give you an error signal over here. It'll go low. Try that. Now, you might say, well, what good is it? Well, I'll tell you what good it is. The possibility of getting 1 error in today's communication systems with the shielded wire, with the twisted pair wire, with the shielding that you have on the motherboards is virtually impossible. But if there is an error, Parity detects it. Therefore, the possibility of getting 2 errors is infinitesimally small. 3 errors is not going to happen. So Parity is very, very useful. If you take a look at page number 94, 4-bit controlled inverters. Exclusive ORs can be used as controlled inverters, and you can see them. I show 2 of them here. And to explain how the controlled inverter works, you can go back and look at page 94, but basically I want to show it this way. I have a exclusive OR gate here, an exclusive OR gate here. If I take one of the lines, let's take line B and let's tie it high and make it a 1. So if we make B 1, here's the truth table for the exclusive OR. We're just looking at this row and this row because that's where B is a 1. See, B is a 1 here. Look what A does. If B is always a 1, A gets fed into the exclusive OR, but the output is always inverted. If A is a 0, you get a 1 out. If A is a 1, you get a 0 out. So whenever one of the inputs to exclusive OR is tied high, the output is always the inversion. You can control that inversion by putting a 1 on the other input, which we're going to do in a minute. If you make it low all the time, you're looking at, if you make, in this case, one of the inputs low, in this case it was B, so we're looking now at these rows where B is 0. Make B 0, make B 0 right here. Notice the output is always the input. A, you get A in the output. 1, you get 1 in the output. 0, 0, 1, 1. So by making this input here, by making one of these inputs low, you pass the signal through. By making it high, you always invert the signal. Now, we can look at page number 94. And on page 94, you can see this 4-bit controlled inverter. Whenever the signal goes high, and you have to look at your exclusive OR truth table. Whenever the signal goes high, it's fed to every one of these inputs. The output is always the inversion of the input. It inverts this nibble, whatever this nibble is. A 1, 1, 1, 1, you get a 0, 0, 0, 0. If it's a 1, 0, 1, 0, you get a 0, 1, 0, 1. If it's a 0, 1, 1, 0, you get a 1, 0, 0, 1. By making this line go low, it just passes the signal through. We're going to use this circuit a lot later on. Naturally, I'm going to call this signature invert. High active. Whenever this line is a 1, it's inverting. When it's a low, it's not inverting. On page number 95, comparator circuits. How can you use exclusive OR for comparator circuits? How would you design a 2-bit comparator that will compare 2 2-bit numbers? And here they are. The least significant bit is A0 and then A1. That's only 0. It only counts 0 through 3. 0, 0, 0, 1. 0, 0, 1, 0, 0, 1, 1, 1. And the same thing over here. 2-bit number. So how would you design a 2-bit comparator circuit that will compare 2 2-bit numbers and produce a high active output signal called equal when the 2 numbers are the same, when these numbers are the same? Well, you could go to a truth table if you want to. But as soon as you hear the word comparator circuit, you can go right, use exclusive OR gates here. Take a look at the design here real quick. When these are the same, okay, this is going to be a 0. And when these are the same, these are going to be a 0. In other words, A0 has to be equal to B0, and A1 has to be equal to B1 in order for both of these to be the same number. So when these are the same, you get a 0, and when these are the same, you get a 0. And a 0 here and a 0 here, you want a high here. And you're calling that equal, high active. Forget about what we're going to make this gate. Just let the story tell you what this gate is. A low here and a low here, you want a high here. You draw it like this. It's a NOR gate. Or you can use exclusive NOR gates down here, okay, which produces a 1 when they're equal. when they're equal. So you see a 1 here and a 1 here is the only time you want a high here. That's an AND gate. Very easy circuits to design, and you can expand this to 3 bits as well. Okay, just by comparing A0, B0, A1, B1, A2, B2. If you have a 4-bit number, A3, B3. How would you change the current circuit up here if you wanted a low active equal? Well, if we wanted a low active equal, all we'd do is put a bubble here. We'd put a bubble. A low here and a low here and a low here. You'd want a low here if you wanted to make a low active signature. So if there's a bubble here, what gate is that? If there's a bubble right here, what gate is that? It's an OR gate. How about down here? Put a bubble on this. It's a NAND gate. It becomes a NAND gate, and there's a bar above that. Either one of these circuits would work. This one uses exclusive OR, this uses exclusive NOR. On page number 96, how would you design a 3-bit comparator with 2 inputs, A2, A1, A0, and B2, B1, B0? It would just expand on the last circuit. Remember? You just expand on this last circuit right here. You'd put an A2 and a B2 here. And you'd have to have a 3-input gate on the output. I'll let you look at that. And here's a 6-bit comparator circuit. I showed you how to generate a 6-bit comparator. Use 1, 2, 3, 4, 5, 6 exclusive NOR gates in this case. You could use exclusive OR. It's just going to change what this output gate is, that's all. Go ahead and design this circuit using exclusive ORs and tell me what that gate's going to be down there. If you use exclusive OR gates right here, whenever they're the same, what's the output going to be? And you need all those to be that state to get the high active output. You can tell me what gate that has to be. Pretty easy to come up with that. I think it is. Page number 97, arithmetic circuits. Exclusive OR and exclusive NOR can be used in arithmetic circuits. We're going to talk a lot about that in week 13. And then on page 98 and page 99, I want you to take a look. I have real quick final designs here, examples for fundamental products. You should look these over. Design a circuit with 3 inputs, A, B, and C, that will produce a high-level output whenever the majority of the inputs are 1s. There's the truth table. Notice the fundamental products here. When the majority of these inputs are 1s, oops, here there's 2, here there's 2, here there's 2, and there's 3. There's the fundamental products, and you simplify that, and there's the circuit. And then finally, on page 99, design a logic circuit that will produce a output Y whenever A and B goes high or C and D goes high. We already worked on this 3 different times. Notice this is the fundamental products for it. This was in a couple lectures ago. Notice the midterms are out here. Here's the shorthand notation we talked about. We're going to start using that in the next lecture. It can be reduced down to this, and then you realize the circuit with 3 gates. That concludes the lecture.